So probability is generally defined, in my opinion, in three possible ways. Okay, the first probability is what is called as classical probability. Right, number of outcomes divided by the total number of possible outcomes. Right, go back. What is the probability that event E1 will take place? So now let us use the notation. I am going to use the notation PR to indicate probability. Probability of what? Probability of event E1. What is E1? The E1 is defined here. Getting an even number on the die, right? Getting an even number on the die, the possible outcomes are 2, 4 or 6. So how many outcomes? 2, 4 or 6. 2, 4 or 6. Divide by all the possible outcomes 1, 2, 3, 4, 5 and 6. So what is the, how many elements in the numerator? 3 elements in the numerator. How many elements in the denominator? 6 elements in the denominator, and therefore what is the probability of event E1? Probability of event E1 is half. Why is it called classical probability? It is called classical probability because I can tell you that the probability of event E1 is half even without conducting an experiment. I don't have to roll a die. I don't have to roll a die to tell you that event E1 will happen with a probability half, because I know the numerator is going to be 2, 4, 6. I know the denominator can be 1, 2, 3, 4, 5, 6. There are 3 possible outcomes that guarantee that E1 has happened. Totally there are 6 possible outcomes. Out of 6, when any of the 3 happen, I say that event E1 has happened. So what was the definition? Definition was number of outcomes where the event has happened, which was 3, divided by the total possible number of outcomes, which was 6. So 3 by 6. Did I actually roll a die? No. I know when you roll a die, either you will get one outcome, something, either you will get a 1 or a 4 or a 5 or a 6 or a 2. And I'll count you only when 2 or 4 or 6 happen, event E1 has happened. And what is the probability of that happening? 2 or 4 or 6, which means that any one of the 3 outcomes can happen. So 3 in the numerator. What are the total possible number of outcomes? 6. Right. So whenever probability can be calculated even without conducting an experiment, that probability is called classical probability. Okay. What is the second definition of probability? Second definition of probability is more empirical, more, right, relative frequency of occurrence. Okay. So now for the same event, chasing the same event, let us say that we conduct an experiment. So experiment is conducted, roll of a die. I decide to do this experiment 10 times, right? I keep on rolling the die. I get 10 outcomes in the 10 iterations of this rolling, right? I have conducted this experiment 10 times. Let us say the outcomes are 1, 4, 5, 2, 6, 3, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, 5, 3. These are the 10 outcomes in the 10 iterations. I actually conducted this experiment, right? Now I am rolling the die physically. Okay, rolling the die physically. Now out of these 10, I count how many times event E1 has happened. This is event E1. What is event E1? Getting an even number, getting an even outcome. When did I get even outcome? This was even, this was even, this was even, this was even, this was even. Okay. So I will say that what is the probability of event even happening? How many times event even happened? 1, 2, 3, 4, 5. Out of 10 experiments, it turned out to be half. I am sorry. It turned out to be half. It need not have, right? One of these 6 one of these 6 could have been easily a 5 and I will get 4 out of 10, right. One of these other things, one of these 3 could have been a 4 and I will get 6 out of 10. So, empirical probability need not always match classical probability. Empirical probabilities are derived from actually on the field observations, which means that you have to conduct the experiment. Okay, you have to conduct the experiment. Let us do this using a simpler example. What happens every time there is a cricket match? I am sorry, I am taking a lot of cricket examples, but we are a cricket crazy nation, so doesn't matter, right. Tossing a coin, right. That is my experiment. Now, what is the probability of a head? What is the probability of a tail? Remember, this is the notation that we had decided to use. PR to represent probability and curly brackets to represent what is the event. So, event of getting a heads, event of getting a tails, those are the only 2 things. Tossing a coin is a fairly simple experiment, only 2 outcomes. Okay, let us say that this coin is a very fair coin. This coin is a very fair coin, which means that it is nicely manufactured, it is nicely balanced, the coin is nicely balanced, which means that it has equal probability to land on a head or land on a tail, right, which means that the probability of head is 0.5, probability of tail is also 0.5. How did we get this 0.5? It is one outcome divided by total possible outcomes 2. There are 2 possible outcomes. Out of this, when I get a head, that is when I say that this event has happened, right. So, similarly, one outcome when the event has happened and 2 possible outcomes, right. So, classical definition. So, I know this, so this is classical probability, this is classical probability. Now, let us say that I conduct a coin toss experiment. Coin toss experiment is conducted 10 times and I observe the outcome every time. So, let us say I get a head on the first coin toss, I get a head on the second coin toss, I get a tail, I get a tail, I get a tail. So, 5 done, head 6, 7, 8, 9, 10. So, 10 possible outcomes from 10 experiments. I could have gotten a different sequence, right. So, if I conduct the experiment once, let us say this is the outcome I get. Let us say I do this twice, second time, which means I again toss the coin 10 times. So, I may get a completely different sequence because the coin tosses are independent, right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what is the probability of heads? 1, 2, 3, 4. 4 heads out of 10 coin tosses. So, it is 0.4. What is the probability of head here? 1, 2, 3, 4, 5. 0.5. So, this is your empirical probability. So, 2 ways of defining probability: empirical probability and classical probability. For classical probability, I do not have to conduct an experiment. Empirical probability, I must conduct experiments, and probabilities are actually derived from experiments. Are these the only 2 ways of defining probability? I will argue that it is not. There is one more way of defining probability, right. Now, I must take the example of cricket again. Remember, we often say that Dhoni was a lucky captain. He used to win a lot of coin tosses. he will always win the toss. I have heard people saying that. How can that happen? Statistically, how can that happen? Coin toss is a random experiment where you get heads or you get tail. Dhoni may call head or a tail depending on whatever he wants to call. Right? Whatever he has called, let us say he has called heads. The coin is not going to listen to him. Statistically, that is just not, logically also that is just not possible. Coin is going to land on head or tail with equal probability if the coin is fair. Right? So, how can we say that one person has the magical ability to match with the actual outcome? Whatever they have called actually turns out to be the outcome. Very unlikely, impossible actually, right? But still people have said that Dhoni is a lucky captain. Why are they saying that? Why are they saying that? They are saying that because there is a third way of calculating probability. There is a third way of calculating probability which is called subjective probability. Subjective probability, right? For example, let us say that you are playing with your friend and you are deciding that you will toss a coin and you will call out, let us say you called out head, and if you get a tail, which means that you lose, you will buy your friend a can of cola. However, if you win, you called out head and the coin actually turns out to be head, your friend will buy you a can of cola. Let us say that this betting happens. As a student of statistics, you know that probability of getting a head and probability of getting a tail is the same, half and half. So, it is a very, very unbiased experiment, so to say. You should say heads 50% of the time, you should say tails 50% of the time. You know what is going to happen? Let us say that this experiment is conducted 3 times. Okay. So, let us say this is the experiment number 1. You called out heads and okay, the experiment is conducted second time. You again called out heads. There are 2 possible outcomes, right? Now, let me tell you the results. Let us say that in the first coin toss, you lost. Second coin toss, you lost, which means that actually the coin toss turned out to be tails. You had called heads, you lost. So, you lost. Again you called out heads, again the coin landed on tail. Now, let us say that there is a third coin toss. You have to call out whether you are going to call out a head or you are going to call out a tail. Most likely you are going to call out a tail. If you are honest with yourself, just think. Most likely you would have called out tails. Why? Last 2 times I got tails here, I lost. I had called out heads and it turned out to be tails. Now I will call out tails. The outcomes are still the same. Not only the outcomes are same, even the probabilities are same. Last 2 times the coin has landed on tail doesn't mean that in the third coin toss the coin is going to land on tail. Some people would have argued the other way. Some people would have called out heads again, giving a very, very biased argument. They would have argued, last 2 times the coin landed on tail, which means that this time it is more likely that it will land on heads. So, I will call out heads and I will bet that this will happen. All the arguments are incorrect because coin tosses are independent. The first coin toss is independent of the second coin toss, is independent of the third coin toss. They have no influence. Coins don't have memories. Coin doesn't remember that last time it landed on tails, right? So, how did you take a decision? Remember, that's what we were consistently talking. Statistics should affect decision making. You have to take a decision whether you are going to call out heads or you are going to call out tails. that decision whether to call out head or tail, you took on subjective probabilities. You thought that it is more likely that since last 2 times it landed on tail, it is likely that it will land on tail now also. So, you assumed a higher probability of getting a tail again, because last 2 times it had tails, right. So, you assumed a subjective higher probability of heads. So, if you called out heads in the third coin toss, if you called out heads, that means that you assume that the probability of tail is bigger than probability of heads. You assume this, and therefore you called out heads, tails. If you betted on heads, if you thought last 2 times I have been saying heads, last 2 times the coin has landed on tails, since last 2 times the coin has landed on tails, this time it is more likely that it is land on heads, because no heads so far, 2 coin tosses, only tails. So, you assigned a higher probability of heads. You assigned a higher probability of heads, and therefore you betted on heads. What are you doing? You are using subjective probabilities. If you had used classical probabilities, you would have said, I don't care. I really don't care. Call out heads, call out tails, it's the same probability. You realize that there is no control. You don't have any control. It's a completely random statistical experiment. So, subjective probabilities are equally important to be considered, right. You have seen a stock price evolve over a period of time. Stock price has gone down, stock price has gone up, right. Now, you have to decide whether you are going to buy the stock today. When will you buy the stock today? You will buy the stock today thinking that you will sell it off tomorrow and make some profit. But for you to make the profit, the stock price should have gone up. So, are you betting on the stock price going up? Why are you betting on the stock price going up? Do you know the probabilities? You don't know the probabilities. So, many times, I am not saying always, many investors take a decision to buy or sell a stock not on classical probabilities, not on empirical probabilities. Many times they take their decisions based on subjective probabilities, and therefore subjective probability is also equally important to be considered, because many times human beings have a tendency to assign probabilities. Even though I cannot calculate, in my mind I cannot calculate the probability, I will assign a value of probability. Okay, let us move on. So, 3 ways of calculating, 3 ways of defining probability: classical probability, when you don't have to conduct an experiment; empirical probability, when the probabilities are calculated only based on the frequency of observation divided by the total number of experiments that we have conducted; subjective probability, it is just subjective, completely your opinion, right. You think that head is more likely, so you bet on heads. You think that it will rain tomorrow without knowing what is the historical data about the weather patterns, without knowing any meteorological models, right. You are deciding, there is a decision to be made. Do you take your umbrella or not? So, if you believe subjective probability of rain is more, you will take the umbrella. If you believe, which means that subjective probability of rain is less, you won't take the umbrella. Once again, decision taken based on subjective probabilities, right. So, 3 ways of defining probability. Once again, what is empirical probability? I have defined that empirical probability here. Empirical probability is probability of a particular outcome is proportion of times the outcome would occur in the long term of repeated observations, which means experiments have to be conducted. This is the empirical probability. This is the second definition of probability. All right, let us take an example. Okay, so this is, I have explained all this here, right. Let us probability is always a number between 0 and 1, right. Probability is always a number between 0 and 1. sum of probability is actually always equal to 1, right, because those are the outcomes. Either you will get a head or you will get a tail. Either you will get a head or you will get a tail. There are no third alternatives there. So, sum of all probabilities have to add up to 1, right. So, when you count outcomes, when you count events, those probabilities do not have to add up to 1, right. Those probabilities do not have to add up to 1. For example, probability of E3 itself is 1. Probability of E3 itself is 1. Getting a number lesser than 7. Probability of any number you get on the roll of a die is always going to be lesser than 7. So, you can always define such a trivial event whose probability itself is 1. Then you say E1, and we have already said that the probability of E1 is half. If you add up all the probabilities, 1 plus 1 half, it is definitely going to go up more than 1, right. So, I am not talking about adding all the probabilities of events. All the probabilities of events need not add up. When you count individual outcomes, what is the probability of getting a 1? What is the probability of getting a 2? What is the probability of getting a 3? What is the probability of getting a 4? What is the probability of getting a 5? What is the probability of getting a 6? Each is 1 by 6. If you add up, it will be 6 by 6 and therefore 1. So, sum of all probabilities of outcomes will be 1. Right. So, this is how the notation is going to be. So, probability of getting a head, probability of getting a tail. Why do I say x equal to? That is a variable, right. What is the outcome? What is x? X is the variable of interest. X is the variable of interest. Now, x can take head as a value, x can take tail as a value. So, if x takes on a value heads or x can take on a value tail, that probability is 0.5 as long as it is a fair coin. Now, the coin itself may be manufactured in a biased way, and therefore, these probabilities may not be 5, may not match. Those are weird cases. Generally, in all the statistical discussions, we assume that the coin is fair coin, right. We generally assume that the coin is a fair coin.